Hello everyone, I am Boite Gauri, Assistant Professor in VPKBIT Paramati. I welcome you all to my video lecture. So this is video lecture for engineering mathematics students, and the topic of my lecture is linear differential equation, and this is my first lecture of this unit, linear differential equation. And in this lecture I cover the basics of linear differential equation, its solution, and mainly I see how to find out the complementary functions CF of linear differential equation. So first, why we learn these differential equations basically? So we know that differential equations are widely used in the field of engineering and sciences. Mathematical modeling of many physical systems like as electrical circuits, then string of vibration or heat transfer through a cylinder or any uniform rod. So if we apply mathematical modeling, so we get mathematical modeling is differential equation. So therefore we must know what are the differential equation, how to find out the solution, and what is the nature of solution or physical significance. Now first, differential equation means the equation which involving dependent variable, independent variable and its derivatives is called differential equation. So see these examples. So d2y by dx square plus y is 0, or x w by x plus y w by y is equal to xy. These are examples. So here depend upon the derivative involving, there are types of differential equation, two types mainly. One is ordinary differential equation. So in ordinary differential equation involve only one independent variable and its ordinary derivative. So here x is independent variable, y is dependent variable, and derivative of y with respect to x. It is first order, it is second order derivative, and their linear combination. Second type is partial differential equation. So in this equation involving more than one independent variable, and so therefore partial derivatives. So equation involving partial derivative kappa 2f by kappa x square plus kappa 2f by kappa y square is equal to 1. Here partial derivatives are involved, so it is partial differential equation. So main difference is here only one independent variable x, here more than one independent variables x and y, here y and t. Okay. So now we are mainly in this unit, in this lecture, dealing with linear differential equation. So what is linear differential equation? So the equation of the form a naught dny upon dx raised to n plus a1 dn minus 1y upon dx raised to n minus 1 plus a2 dn minus 2y upon dx raised to n minus 2 plus so on an minus 1 dy by dx plus any is equal to f of x. So differential equation of the form where derivatives occurs in the addition form and its coefficients are a0, a1, a2, an, which are either constant or function of x, is known as linear differential equation. Linear means all derivatives occurs in the form of addition. So see here example, d2y by dx square plus 5 dy by dx plus 6y is equal to 0. So y dy by dx, d2y by dx square appear in the form of addition. There is no multiplication term y dy by dx like this. So it is known as linear when it occurs in the form of addition. Differential operator or derivatives occurs in the form of addition, and here coefficients are 1, 5, 6, 6, 5x, 6. So coefficients are constant, some are functions of x. In second example, d2y by dx square plus y is equal to e raised to x. So here coefficient is 1, coefficient of dy by dx is 0, coefficient of y is 1. So all are constant and RHS is function of x e raised to x. Okay. So sometimes RHS may be function of x, sometimes it might be constant. Now if all coefficients are constant, then we say that linear differential equation with constant coefficient. Okay. Now there are different notations used to write derivative. So different notations for differential equation also. So suppose y2 minus d2y by the differential equation d2y upon dx square plus 1 is equal to 0. So this differential equation also has d square y plus 1 is equal to 0, or we can use another notation y double dash plus y is also equal to 0. So these are the different notations used for derivative. These are the same difference. Okay. Now we are using this standard derivative notation y, then dy, capital capital Y, d cube y. So our differential equation, linear differential equation, a naught dn y upon dx raised to n plus a1 dn minus 1 y upon dx raised to n minus 1 plus so on an minus 1 dy by dx plus an y is equal to f of x. In this equation, I use dy by dx is capital D, d2y by dx square is capital D square, dny by dx raised to n is capital D. So above differential equation is in this form: a naught d raised to n plus a1 d raised to n minus 1 plus a2 d raised to n minus 2 plus so on an minus 1 d plus an into 1 is equal to f of x. So we can write this differential equation as first term is phi of the polynomial in D into y is equal to f of x. So any differential equation is given in any form, we use capital D notations for derivative and we convert it into phi of D into y is equal to f of x. So let us see one example. Suppose my differential equation is given d2y by dx square plus 4 dy by dx 4 dy by dx plus 4y is equal to 0. So this differential equation I can write d square plus 4d plus 4 is equal to 0. So every differential equation we can write into y into y is equal to 0. So every differential equation we can write phi of d into y is equal to f of x, whatever the RHS function. Okay. Now we see auxiliary differential equation. So what is auxiliary differential equation? So for every differential equation, we can write phi of d into y is equal to f of x. Then the coefficient of y, which is polynomial in d, if we equal to 0, we get corresponding auxiliary equation. Okay. So see the 4 d cube y by dx cube minus 6 d square y by dx square plus 4y is equal to 0. So I can write this differential equation in the standard form or in the form of capital D. So 4d cube minus 6d square plus 4 into y is equal to e raised to x. So this is my phi of d into y is equal to f of x. So how we write auxiliary equation? Just I equate this phi of d part to 0. So phi of d is my 4d cube minus 6d square plus 4 is equal to 0. I equate it to 0, whatever the RHS term. But in auxiliary equation, I equate this phi of d to 0. We are getting auxiliary equation. So understand how to obtain. Okay. So let us see example. Suppose my differential equation is d square plus 9 into y is equal to 3x. But what is my auxiliary equation? This is my phi of d, and I equate this phi of d polynomial in d to 0. So phi of d is equal to 0. So my auxiliary equation is d square plus 9 is equal to 0. This is my auxiliary equation. Okay. So everybody can find out auxiliary equation from any given differential equation. Okay. Now we see homogeneous and non-homogeneous differential. So if differential equation is phi of d into y is equal to f of x, and if RHS function is 0, in this case it is known as homogeneous if RHS function is 0. For example, d2y by dx, dy by dx plus y is equal to 0. So RHS term is 0, so it is homogeneous. And non-homogeneous differential equation. So if RHS function is non-zero, f of x is non-zero, then it is non-homogeneous equation. So here it is e raised to 2x non-zero function. So it is non-homogeneous differential equation. Okay. So homogeneous means RHS function is 0. Non-homogeneous means RHS function is non-zero. So suppose we have some examples. So we identify which is homogeneous and which is non-homogeneous. So here my RHS function is x minus 2 and it is non-zero. So therefore it is non-homogeneous. Okay? It is non-homogeneous. In second example, if you observe d2y by dx square plus 3dy by dx plus 2y minus 3x square term is there. So if I shift to RHS, it becomes equal to 3x square and it is non-zero term. So my f of x in the standard form, we shift constant terms of f of x term to the RHS, and it is my standard form a naught d2y by dx square plus a1 dy by dx plus a2y is equal to f of x. So here it is non-zero, and therefore again this is also non-homogeneous differential equation. In third example, there is no constant function in LHS as well as RHS, and RHS is 0, so therefore it is homogeneous differential. And fourth one, it is non-zero function, so again it is non-homogeneous differential equation. So if you understand this, the function, even if we look here 0, but constant term appear in LHS, we shift it to RHS, it becomes non-zero. So except third, only this is the homogeneous differential equation. Remaining all are non-homogeneous differential equation. Okay. Now we see what is the solution of differential equation. So solution means it is the relation between dependent and independent variable which satisfies given differential equation. So for example, my differential equation is d2y by dx square plus y is equal to 0. So If I substitute y is equal to sin x or y is equal to cos x, what happens? We know the derivative of sin x is cos x and second derivative is, so y dash is equal to, here we get y dash, first derivative becomes cos of x and second derivative becomes minus sin x. So when I substitute d2y by dx square means minus sin x minus sin x plus y is sin x. So minus sin x plus sin x get cancelled and I get resultant value is 0. So this relation y is equal to sin x satisfies given differential equation. Therefore, it is the solution of differential equation. Similarly, you can check for y is equal to cos x. First derivative is minus sin x, second derivative is minus cos x, and then minus cos x plus cos x 0. So this is also solution. Similarly, sin x plus 2 cos x is also solution. So if this is second order differential equation, we are having sin x is one solution, cos x is another solution, sin x plus 2 cos x or cos x plus 2 sin x, all are the solutions. So how many solutions or what is the solution? So there is one general solution is there. The general solution is given y is equal to c1 into sin x plus c2 into cos of x. And I getting all these solutions if I give particular values to this arbitrary constant. Here c1, c2 are arbitrary constants. So if I put c1 is 1, c2 is 0, I get this first solution. If I put c1 0, c2 s, I get cos x. If I put c1 1, c2 2, I get 2. So arbitrarily you substitute the value of c1, c2 for any combination. There are infinite solutions, but general solution is unique, which is c1 sin x plus c2 cos. Okay. So in this we are seeing how to find out the general solution of given differential. So if y of d into y is equal to f of x, it is the linear differential equation, then there is general solution for this differential equation, and the general solution contains two parts. One is complementary function and another is particular integration. Okay. So general solution of differential equation, linear differential equation, y of d into y is equal to f of x contains two parts. First part is known as complementary function, that is denoted as CF or y suffix tyc. Second part is particular integration. This is known as pi or y. Okay. So general solution is given CF plus pi or y is equal to yc plus y. So what is complementary function or CF? So this is the solution of corresponding homogeneous differential equation. So when we are finding solution of y of d into y is equal to 0, the solution corresponding to homogeneous differential equation is called complementary function, and the particular integration is the function such that when I operate this phi of the operator on yp, I am getting this f of x function. So this is known as my particular integration. What is pi? It is not corresponding to homogeneous solution. It is a function such that when I operate phi of t on yp, I am getting resultant function f of. Okay. So we can write yp is equal to, take this 1 upon phi of t here, you get f of x. Now note the point. If differential equation is of nth order, then its complementary function or CF contains n arbitrary constants, which are saying C1, C2, Cn. and particular integration does not contain any arbitrary constant. Okay. So if differential equation is homogeneous, then its particular integration is 0, RHS function is 0, so f of x is 0, and therefore what is the formula for P and C? 1 upon phi of d into f of x. So this homogeneous means f of x 0. So if f of x is 0, 1 upon phi of the f of x is 0, and therefore particular integration is 0, and general solution is CF plus PI, but PI is 0, so general solution is only equal to 0. Okay. Now before go to this method for finding CF, I would like to explain what is CF and what is PI. Okay, or first we see method for finding complementary function. So for any differential equation, we know we can write phi of d into y is equal to f of x. Then first step is find auxiliary equation of given differential equation. So if phi of d into y is f of x, its auxiliary equation is phi of d is equal to 0. Second step is find the roots of auxiliary equation. Then after finding the roots of this auxiliary equation, we decide the nature of complementary function, and the complementary function or nature of complementary function is dependent upon the nature of roots. Okay. Now we know that if it is the nth order differential equation, then phi of d is n degree polynomial, and if it is n degree polynomial, it has n roots. So, and it contains complementary function contains n arbitrary constant. Okay. Now we see the natures of roots. So how many types of roots are there for any polynomial? So normally there are 4 types. First is roots are either real and distinct. Sometimes roots might be real and repeated. Sometimes complex and distinct. Sometimes complex and repeated. For some polynomial, we have a combination of these roots also. Some roots are real, some are complex. Some roots are real and repeated, some roots are real and distinct. But mainly the types of roots we divide into 4 parts. First is real and distinct roots. Second is real and repeated. Third is complex and distinct. Fourth is complex and repeated. So according to these 4 types, we are writing is complementary function. So let us see first example. Roots are real and distinct. So if m1, m2, mn are real and distinct roots of the auxiliary equation, what are the roots? Real and distinct. Then its complementary function is c1 e raised to m1x plus c2 e raised to power m2x plus c3 e raised to m3x plus so on cn e raised to mn. So if there are n roots which are real, then its complementary function contains n arbitrary constants c1, c2, cn, and coefficients are e raised to m1 times x plus e raised to m2 times x plus e raised to m3 times x plus cn e raised to mn times. Okay. So let us see one example. If d is equal to 1 and d is equal to 3, these are the roots of auxiliary equation. Obviously, this is real and distinct root. So what is the nature of complementary function? Suppose m1 is 1, m2 is 2. So our CF is, how we write CF? C1 times e raised to m1x, so e raised to 1x, plus C2 times e raised to m2x, so C2 e raised to 3x. So this is the equation or complementary function if root is 1 and 3. So somebody can write C1 e raised to 3x plus C2 e raised to x, no problem. This is also correct complementary function. You can increase the order of roots. This is also correct because C1, C2 are arbitrary constant. So I recall again, if M1, M2, Mn are real and distinct, that means it appear one time, then its complementary function CF is C1 times e raised to M1x plus C2 times e raised to M2x plus C3 times e raised to M3x and Cn times e raised to Mn. So suppose, again I will take suppose D is equal to 2, 5. These are the two distinct real roots. So what is CF we write? CF is equal to, for first we write first arbitrary constant C1 e raised to 2x plus for second constant C2 e raised to this 5x. Okay? So these 2 and 5 occur here in the exponential times x. 5 times x, 2 times x. Okay? So in this way, if roots are real and distinct, we are writing corresponding complementary function or contribution in the here. Now second case we see roots are real and distinct. So if M1, M2 are same roots and remaining roots are distinct, then what is the corresponding complementary function? So for repeated root, if this root occurs 2 times, so corresponding CF contains two arbitrary constants. First is C1 plus C2 times x into e raised to repeated root M1x plus C3 e raised to M3x plus C4 e raised to M4x plus Cn e raised to Mn. These roots are occurs one time, so only the contribution is of this type. But here M1 root occurs 2 times, so its coefficient contains two arbitrary constants and method is C1 plus C2 x. Suppose some another root occurs 3 times. M1, M2, M3 are same. It means M1 root occurs 3 times. Then its complementary function or contribution in complementary function is C1 plus C2x plus C3x square e raised to M1 x. And if remaining roots are occurs one time, so corresponding to it is C4 e raised to M4x plus Cn e raised to Mn. Okay. So for example, D is equal to 2. This root occurs 2 times. That means D is equal to 2, D is equal to 2. Real and repeated root. So what is this complementary function? C1 plus C2x into e raised to 2x. Okay. So I hope you understand case 2. Now case 3, if roots are, another example is this, 1, 1, 1 root, it occurs 3 times. Its contribution in CF is C1 plus C2x plus C3x square into e raised to x. Now next we see roots are complex and distinct. So we know that complex roots are always occurs with continuous pairs. So if M1 is equal to alpha plus I beta is root, definitely M2 is equal to alpha minus I beta is also root. So what is the auxiliary nature of complementary function here? So if roots are alpha plus I beta, alpha minus I beta, real part is alpha, imaginary part is beta. So CF is equal to y is equal to e raised to alpha x e raised to power real part times x into bracket C1 cos of beta x plus C2 sin of beta x. Okay. So this alpha is real part of that complex number. This beta corresponding to imaginary part of that complex. So CF is e raised to real part of root into C1 cos of imaginary part times x plus C2 sin imaginary part times let us see example. If roots of auxiliary equations are 2 plus 3i, 2 minus 3i. So obviously roots are complex and distinct that occur one time, and real part alpha is 2. Imaginary part, we forget about this sign. Imaginary part is always positive. It is 3. So therefore here CF is equal to e raised to 2x alpha times x into C1 cos of 3x plus C2 sin of 3x raised to alpha x C1 times cos of beta x, that is 3x plus C2 sin of beta. So in this way, if roots are complex, we get solution in terms of exponential plus additional cosine. If roots are real, we get only solution in terms of complex, exponential. Now case 4, if roots are complex and repeated. So let M1, M is equal to alpha plus I beta and alpha minus I beta, and these roots occur 2 times. Okay. Then what is the complementary function? So e raised to alpha x into bracket C1 plus C2x times cos of beta, because alpha plus I beta occurs. Right? So C1 plus C2x cos of beta plus C3 plus C4x into sin of beta. So C3 plus C4x into sin of beta. Okay? So when root occurs 2 times, its arbitrary constant contains the term C1 plus C2x of this x. So alpha plus I beta occurs 2 times, alpha minus I beta occurs 2 times. So there are 2 terms, C1 plus C2x cos beta x plus C3 plus C4x sin beta x into this e raised to real part times e raised to alpha. Now, suppose we having roots of auxiliary equations are 1 plus 3i, 1 minus 3i, 1 plus 3i, 1 minus 3i. So roots are clearly complex and repeated. And what is real part alpha is 1. Imaginary part beta is 3. So by comparing this, CF is C1 plus e raised to 1x C1 plus C2x cos of 3x plus C3 plus C4x sin of 3. Okay. So in this way, depending upon the nature of roots, we are writing its complementary function. So just recall this. If roots are real and suppose two roots are there, what is it here? C1 e raised to m1x plus C2 e raised to m2. Suppose there are three roots, then complementary function is still arbitrary constant. C1 e raised to m1x plus C2 e raised to m2x plus C3 e raised to m2. Now second case, if roots are repeated. So if m1 is equal to m2 and it occurs 4 times, then its complementary function is C1 plus C2x e raised to m1x. So you can write this C1 plus C2x into e raised to common root, whatever m1, m2 are there, e raised to mx. Okay, repeated. Suppose it occurs 3 times, its coefficient is C1 plus C2x plus C3x square into common root e raised to mx. Or you can multiply inside, you can write in this way, no problem. Now case 3 is roots are complex roots and distinct. So we know complex root always occur with conjugate pairs. So alpha plus I beta is root, alpha minus I beta. So there are 2 roots. So there are 2 corresponding C complementary function and arbitrary constant in CF. So nature is e raised to alpha times x C1 cos beta x plus C2 sin beta. Okay. So suppose real part is 0, alpha is 0. So e raised to 0x means 1. So if it is purely imaginary number, so 0 plus I beta, in this case complementary function is only C1 cos beta x plus C2 sin beta x, because e raised to 0x means 1. And if roots are imaginary or complex and repeated, in this case, here we replace this C1 by C1 plus C2s and this C2 by C3 plus C4. If it occurs two times, if it occurs two times, then it is C1 plus C2s plus C3x square plus C4 plus C5x plus C6x square. Of this type of term we add. Okay. So I hope you understand this complementary function nature, and it is mainly depend upon the nature of roots. So 4 cases we see: real and distinct, real and repeated, complex and distinct, complex and repeated. So let us see example. Find complementary function of the differential equation d square minus 5d plus 6 into y is equal to 2x plus 3. So if we observe, this is the function differential equation of the type phi of d into y is equal to f of x. This is my phi of d, this is my y, and this is my f of x. So what are the steps for finding complementary function? We are finding first is auxiliary equation. So what is the auxiliary equation? Auxiliary equation, we equate phi of d to d. So phi of d is d square minus 5d plus 6 is 0. So step 1, find auxiliary equation. Step 2, find out the root. So roots of this equation are d is equal to 2, d is equal to 2. If we don't know how to find out the roots, you can take my subscribe my channel. There is one video I prepared how to find out the roots of cubic and quadratic polynomial. Also, there is another video how to find out the roots by using calculator. So I will share the link in my description box. Now here we get d is equal to 2, d is equal to 2. It's a real and distinct. So therefore it is case first. And what is the complementary function? C1 e raised to m1 x e raised to x plus C2 e raised to e. So roots are real and distinct. Complementary function is C1 e raised to 2x plus C2 e raised to e. Let us see another example. d3y by dx cube plus 6d2y by dx square plus 11dy by dx plus 6y is equal to 0. So given differential equation, we can write d cube plus 6d square plus 11d plus 6 into y is equal to 0. Or it is given homogeneous. Now its auxiliary equation, we equate this phi of d to 0. So d cube plus 6 square plus 11d plus 6 is 0. This is polynomial unity and it is cubic polynomial. So we find out its roots. So roots of this polynomial is minus 1, minus 2, minus 2. Can not see here. So all roots are real and all are distinct. So case 1. So what is the complementary function by using this one? C1 e raised to CF is, or I write YC is equal to C1 e raised to m1x, that is minus x, plus C2 e raised to minus 2x plus C3 e raised to minus 3x. Okay, so you can see the solution. C1 e raised to minus 1 times x plus C2 e raised to minus 2 times x plus C3 e raised to minus 1 times x. Okay. Now another example. d2y by dx square plus 6dy by dx plus 9y is equal to 2x. So given differential equation, we write in capital D form d square plus 6d plus 9 into y is equal to e raised to 2x. So what is my phi of d? d square plus 6d plus 9. Okay. So this is my phi of d. function. This is my phi of d, and I equate the phi of d is 0. Whatever the arrangement, I am not interested. Then this is polynomial, quadratic polynomial in D. We are finding roots. So what are the roots? D is equal to minus 3, D is equal to minus 3. Actually, it is the expansion of d plus 3 bracket square. And roots are real and repeated. So case 2 is there. And complementary function is c1 plus c2x e raised to minus 3x. Okay. Now, next example, d cube minus 2d square plus d into y is 0. So, auxiliary equation is d cube minus 2d square plus d is 0. We are not taking y in auxiliary equation. So, we get only polynomial in d. So, we find the roots. So, roots we are getting, if we take d outside, d is equal to 0 is one root. And another d square minus 2d plus 1. So, it is d is equal to 1, d is equal to 1. So, one root is occur one time, that means it is distinct, and one root is repeated. So, it is the combination of real repeated and real distinct roots. So, corresponding 0, 1 is plus plus 1. Okay. So, in this way, we can help combination of real repeated and the first one is distinct roots, second one next constant number. Next is d2y by dx square plus 4y is 0. So, auxiliary equation is d square plus 4 is equal to 0. And roots of this equation are d is equal to plus minus 2y. So, it means 0 plus minus 2y. So, it is complex and which are distinct. So, therefore, case 3, its CF is e raised to alpha and cos beta is 6. So, alpha is 0, beta is 2, and we know that e is 1. So, it is the c1 cos 2x plus c2 sin 2. Okay. Another equation is d square plus 2d plus 2 is equal to 0. So, auxiliary equation is d square plus 5 is 0. Roots are minus 1 plus minus 2y. So, here complex alpha is minus 1, beta is 2. So, by case 3, complementary function plus alpha is c1 cos beta is plus c2 sin beta is. So, it is e raised to minus 1x c1 cos of 2x plus c2 sin of 2x. Okay. Now, here we having d raised to 4 plus 4d square plus 4y is equal to 0. So, auxiliary equation is d raised to 4 plus 4d square plus 4. So, this is nothing but the bracket square of d square plus 2 bracket square. Expansion is a square d raised to 4 plus 2ab, 2 into 2 4d square plus b square, 2 square is 4. Now, we get here roots are 0 plus minus root 2y, 0 plus minus root 2y. This factor occurs 2 times. So, roots also occurs 2 times. So, here we get roots are complex and repeated. So, complex and repeated means case 4. So, alpha is 0, beta is root 2. And how many times it occurs? 2 times. So, e is 1 plus cos beta plus so, substitute that alpha is 0 and beta is root 2, we get 5. So, one more example. Now, it is constant. Minus 1, minus 3 plus minus 3 is constant. So, this constant C1 e raised to minus x plus e raised to alpha x minus C2 cos x minus sin x. E raised to minus x C1 plus C3 times e raised to minus. So anyway you can write solution. No problem. Numbers are here and there. Only how many are there? That many arbitrary constant contains in your solution. Okay. So here are again combination. Roots is 0, 1, minus 1, plus I, minus I. So roots first three are real, last two are constant. So, real root contains exponential factors. C1 e raised to 0x plus C2 e raised to 1x plus C3 e raised to minus x plus due to complex root alpha is 0 e raised to alpha x. Next constant C4 cos of beta x. Beta is 1 plus C5 sin of beta x. Okay. So in this way e raised to 0x is 1. So it is C1 plus C2x plus C3 e raised to minus x plus C4 cos x plus C5 sin x. So in this way we having any combination of roots, we can write its complementary function. Just I recall the factor. What we write? If roots are real and distinct, its contribution is exponential function. If roots are complex, it contains exponential as well as sin and cos term. So I hope you understand. So if you understand, comment box. Okay. So thank